Hello and welcome to the video presentation of our work, Is More Autonomy Always Better? Exploring Preferences of Users with Mobility Impairments in Robot-Assisted Feeding. This work was done in the Paul G. Allen School of Computer Science and Engineering at the University of Washington. Let's start by motivating the problem. 12.3 million people with disabilities in the US needed assistance with activities of daily living, or ADL. In the slide, we showed two videos of caregivers and recipients during a feeding activity. As a key ADL, the primary function of feeding is to nourish the body, but care recipients often reject assistance or may feel uncomfortable with it because of the complex association that food and meals have with self-identity, cultural values, and family life. This is also reflected in some of the challenges associated with caregiver-based feeding, where care recipients lack control or independence during the meal. Robots have the potential to increase or prolong unassisted living for people with mobility impairments by facilitating ADLs. In this slide, we show a video highlighting the components of our robotic system ADA. We start with the JCO2 arm, which holds a custom 3D printed fork holder, instrumented with a tactile sensor, and has a custom vision system mounted on the wrist, which includes a RealSense camera and an NVIDIA Jetson Nano for wireless transmission. The system uses visual and haptic modalities to perform the three phases of the feeding task: bite acquisition, bite timing, and bite transfer. Three redundant levels of safety were implemented based on bounding boxes, low force threshold, and operator proximity. Despite great strides taken towards sustainable solutions in commercial and research environments, autonomous robotic products are far from ready for adoption. Some of the challenges that we will address during this talk are related to the system dealing with varying user preferences, varying environment contexts, and the possibility of error in uncertain and unstructured environments. This work explores end-user preferences for different autonomy levels in a robot-assisted feeding system and investigates the impact of challenges associated with automation errors and need for user input in the context of robot-assisted feeding. Let's delve a little deeper in these challenges for RAF systems in the real world. For varying user preferences, we will consider different user interfaces, different speeds, and different levels of autonomy. For the first user preference we show two interface variants developed for our system, bidirectional voice and bidirectional web GUI, which are shown side by side in this video I'll play next. On the left, we show the voice interface, which uses the Amazon Echo Dot and the Alexa voice service, where a full command contains the hot word, the skill, and the command. On the right side, we show a participant using an assistive device, a sip and puff in this case, to interact with our web GUI.
What would you like?
Alexa, tell the robot to get a cantaloupe.
One cantaloupe coming right up.
Another user preference we focused on is robot speed. This video shows two users interacting with the robotic system operating at different speeds. On the left, we show the fast setting at 0.8 radians per second, and on the right, we show the slow setting at 0.3 radians per second. The last user preference we addressed in this work is the level of autonomy. Our robotic system can operate in three distinct modes of operation. The feeding task always begins with the user selecting a food item using one of the available interfaces. Then there are three phases. First, complete bite acquisition by choosing if the skewering will be vertical or tilted. Then, determine how to transfer the item to the user by choosing between horizontal or tilted approach. And third, determine the timing to approach the user, which can be by detecting the opening of the mouth or by user input. In full autonomy mode, the robot chooses an option for all phases. In low autonomy, the robot requests user input in all phases, and in partial autonomy, only one phase is automated at the time. As an example, here is a video showing a low autonomy trial with a user controlling the system through the web interface. He is using a neck-activated switch. Now let's discuss different environment contexts that may present a challenge for a RAF system. In this work, we considered dining scenarios. In this slide, we show two side-by-side videos of a user interacting with the robotic system. On the left, we show an individual dining scenario, and on the right, we show social dining, which could mean having a meal with a caregiver, a family member, or a friend. This was used for our first experiment, where we studied the preferences in design parameters and social contexts. We set the robot to fully autonomous operation mode. We modified the following independent variables: speed between slow and fast, environment between individual and social dining, and the interface used between web and voice. We had 10 participants, mostly with spinal cord injuries, and 1 participant who indicated arthrogryposis as their mobility limitation. We also grouped our participants considering their mobility limitation. 6 out of the 10 participants had higher mobility limitations than the others. This was also introduced as a factor in our analysis. I will not go into too much details for the results, but I invite you to check out our paper. In terms of interface, we saw flipped preferences depending on the social context. Users significantly preferred voice for individual dining, but preferred web for social dining. In terms of speed, we found no significance, but we saw trends that during individual dining, users preferred faster speeds. During social dining, that preference is lost. We believe it could be confounded since our participants were distracted engaging in a conversation. Now let's discuss the last of the challenges for autonomous assistance we are covering with this work, which relates to the possibility of errors in uncertain and unstructured environments. This is evidenced through system errors in any of the feeding phases: acquisition, time, or transfer. Here we have 3 videos showing each of these errors. For bite acquisition, we show failing to pick up a food item. For bite timing error, we show a user giving the signal that she is ready for the bite by opening her mouth, and the robot delays the response of moving towards the user. And for transfer error, we see the user giving a touch-based input to signal that she's ready for the bite, and the robot delivers the food to a different location. Then it corrects itself and presents the food to the user's mouth. This was used in our second experiment, where we studied preferences in level of autonomy at the risk of errors. We set all other parameters to fast, speed, individual dining, and web interface. We varied the level of autonomy and the presence of errors. We showed low autonomy and partial autonomy. We also intentionally introduced errors in the autonomous phase, and the robot corrected itself after 1 try. So participants saw 7 trials each: low autonomy, and 6 partial autonomy, first without error and then with error. Among the highlights of the results, we saw that more autonomy is not necessarily rated higher, although participants considered low autonomy trials to require more effort compared to fully autonomous trials, and partial autonomy does not help reduce the effort. We also saw significant differences in higher rating responses from users with high mobility limitations. After the experiments were done, we conducted a post-task questionnaire in the form of an interview. These are some of the responses related to how the system could improve the participants' independence. Among them,
every little thing I can do on my own is very important to me. And feeding isn't a little thing, it's a huge thing, so it's very important.
There is a remarkable amount of independence with it.
For the take-home message, we want to say that robot-assisted feeding technology has complex social, cultural, and self-identity implications, since a meal extends well beyond the functional requirement of nourishment. This is highlighted by studies including participants with mobility limitations, which provide interesting insights about their preferences on various factors surrounding human-robot interaction during the feeding task. Instead of designing stiff systems, we as engineers can provide multiple options of use, such as different operation speeds and modes of interaction, as well as implementing different levels of autonomy because their usage is dependent on the changing environmental contexts of the target users. We also have a publicly available video in YouTube if you would like to share this project outside the conference. You can find it by its title, Evaluating an Assisted Feeding Robot with Users with Mobility Limitations. Thank you for your attention, and we will address questions and feedback through email.